Okay, here we are back at another Math Notes 4.2.4. We're going to talk about correlation coefficients. The correlation coefficient R, is a measure of how much or how little the data is scattered around the LSRL. So let me just highlight that here. R is the variable that we use for the correlation coefficient. It is a measure of the strength of a linear association. The correlation coefficient can take on values between -1 and +1. If R equals 1 or R equals -1, the association is perfectly linear. I need to switch that color. All right. There is no scatter about the LSRL at all, if that's 1 or -1. A positive correlation coefficient means the trend is increasing, the slope is positive, while a negative correlation means the opposite. A correlation coefficient of 0 means the slope of the LSRL is horizontal and there is no linear association whatsoever between the variables. Let's unpack that a little bit before we go on to the rest of it. We have some data. Let's see, we have some data that looks like this. We just kind of have a shotgun of data all over the map there. If we come through with the LSRL and we try to find a linear coefficient, or sorry, least squares regression line, then we're just going to get a flat line like that. There's no relationship. This line is going to have an R value of something very close to 0. Now, if we find that there is actually some positive correlation, in other words, the Y value is going up as we increase the X value, but it's still pretty scattered, we can come and put a line between there, but we're going to have a pretty low positive correlation. I'm going to make a number up. We're going to call it positive 0.4. Now, if I had that same sort of style of data, but it was going in the other direction, still pretty spread out, but generally kind of moving down. Now we're going to look at a correlation coefficient of, say, I'm just kind of making this up, negative 0.4. Okay, now if those dots start to get tighter together, I'm going to move these out of the way. So we call this, by the way, a weak correlation. That would be a pretty weak correlation. If those points start to come together and be a little bit tighter, so say we get something like this, now it's pretty clear that those guys are moving in a positive direction. If we put our LSRL through it, would be that. The residuals would be pretty low. We might have an R value on that of like 0.9. And if it was exactly on the dot, in other words, the points were exactly linear and we could come in and fit a line that went through all of them, that's when you get an R value of 1. And if they're going in the other direction, you get a negative R value. Oop, that's not a perfect correlation because the dots don't touch the line. I am doing this by hand. So we're going to pretend all of those dots perfectly touch the line. So this would be a weak association or weak correlation. This would be a strong association or correlation, and this would be a perfect association or correlation. This would be a positive on the top, and this would be negative on the bottom row. That is an amazing word, posite. See if we can spell that. Positive. And this would be no association or correlation. Have an R value of 0. So, the closer to 0, the weaker the association. The closer to 1, the stronger the association. If it has a positive slope, it's going to have a positive R value. It has a negative slope, it's going to have a negative R value. Let's go back to the notes. So, the correlation coefficient does not have any units, so it is a useful way to compare scatter from situation to situation, no matter what the units of the variable are. So you can use this for any graph, and if you have a 0.4 on one graph, it's going to be equivalent to 0.4 on another graph. It's you get a sense of how good the correlation is between those. The correlation coefficient does not have any real-world meaning other than as an arbitrary measure of strength. However, if we square it, the value of the correlation coefficient gains real-world meaning. The R squared is actually more common in sort of practice in the real world than the R value, as far as what people refer to. The R squared value, which is the correlation coefficient squared, is written as R squared and expressed as a percent, has the meaning that the R squared percent of the variability of the dependent variable can be explained by a linear relationship with the independent variable. That is a weird sentence. I'll tell you what it means a little more when I can give you an example. Alright, so for example, here we are. If the association between the amount of fertilizer and plant height has a correlation coefficient R of 0.6, then we can say that the R squared, first off, is going to equal 0.6 squared, which is going to be 0.36, which will be 36%. So we can say that 36% of the variability in plant height can be explained by a linear relationship with the amount of fertilizer used. So in other words, the fertilizer used accounts for 36% of the variability of the plant. The rest of the variation in plant height is explained by other variables, such as the amount of water, the amount of sunlight, the soil type, and so forth. The correlation coefficient, along with the interpretation of R squared, is used to describe the strength of a linear association. So there's something else that happens when we use the R squared instead of the R, and that is that everything becomes positive. You never have any negative R squared values. If we were to go back to this little thing I drew here, then our R squared would be 0.4 times 0.4, or 0.16, positive 0.16. But this would also have positive 0.16. Because when we square a negative, we get a positive. So the R squared on this becomes 0.81. Interestingly, 1 squared is still 1. Negative 1 squared becomes positive 1. And negative 0.9 squared becomes positive 0.81. So you lose the ability to know whether you have a positive or a negative association when you use the r squared, but you gain a real-world interpretation in using it. And so it's much more common for people to use the r squared. Also, r squared is 0. Guess what? Still 0. So the r value can go from 1 to -1. The r squared just goes from 1 to 0. So I have a little joke here from the online comic XKCD. It says, I don't trust linear regressions when it's harder to guess the direction of the correlation from the scatter plot than to find a new constellation on it. In other words, if you get an r squared 0.06 and someone tries to make any kind of statement about what that data means, you probably shouldn't listen to them, because that is super close to 0 and you're not really going to drive a lot of meaning other than the two variables are not correlated. And so that is his warning. And here's Rexar, the dog bearer. Rexlor. All right, so back to our table of studying hours versus grade on that test we've done in the last 2 math note videos. I want you to interpret the r squared value of the following graph. So we have the r and the r squared. Interpret the r squared value. You know what? I'm going to say and the r value. So tell me what that r of 0.818 means and what the r squared of 0.669